In this video, I'm going to introduce principal components analysis, which is a very widely used technique in signal processing. The idea of principal components analysis is that high-dimensional data can often be represented using a much lower dimensional code. This happens when the data lies near a linear manifold in the high-dimensional space. So the idea is, if we can find this linear manifold, we can project the data onto the manifold and then just represent where it is on the manifold. And we haven't lost much, because in the directions orthogonal to the manifold, there's not much variation in the data. As we'll see, we can do this operation efficiently using standard principal components methods, or we can do it inefficiently using a neural net with one hidden layer where both the hidden units and the output units are linear. The advantage of doing it with a neural net is that we can then generalize the technique to using deep neural nets in which the code is a nonlinear function of the input and our reconstruction of the data from the code is also a nonlinear function of the code. This enables us to deal with curved manifolds in the input space. So we represent data by where it gets projected on the curved manifold, and this is a much more powerful representation. In principal components analysis, we have n-dimensional data, and we want to represent it using less than n numbers. And so we find m orthogonal directions in which the data has the most variance, and we ignore the directions in which the data doesn't vary much. The m principal directions form a lower dimensional subspace, and we represent an n-dimensional data point by its projections onto these m directions in the lower dimensional space. So we've lost all information about where the data point is located in the remaining orthogonal directions. But since these don't have much variance, we haven't lost that much information. If we wanted to reconstruct the data point from our representation in terms of m numbers, we would use the mean value for all the n minus m directions that are not represented. And then the error in our reconstruction would be the sum over all these unrepresented directions of the squared difference between the value the data point had on that direction and the mean value on that direction. This is most easily seen in a picture. So consider two-dimensional data that's distributed according to an elongated Gaussian like this. The ellipse is meant to show a kind of one standard deviation contour of the Gaussian. And consider a data point like that red one. If we used principal components analysis with a single component, that component would be the direction in the data that had the greatest variance. And so to represent the red point, we'd represent how far along that direction it lay. In other words, we'd represent the projection of the red point onto that line, i.e. the green point. When we need to reconstruct the red point, what we'll do is simply use the mean value of all the data points in the direction that we've ignored. In other words, we'll represent a point on that black line. And so the loss in the reconstruction will be the squared difference between the red point and the green point. That is, we'll have lost the difference between the data point and the mean value of all the data in the direction we're not representing, which is the direction of least variance. And so we'll obviously have minimized our loss if we choose to ignore the direction of least variance. Now we can actually implement PCA, or a version of it, using backpropagation, but it's not very efficient. So what we do is we make a network in which the output of the network is the reconstruction of the data, and we try and minimize the squared error in the reconstruction. The network has a central bottleneck that only has m hidden units, and those are going to correspond to the principal components, or something like them. So it looks like this. We have an input vector, we project that onto a code vector, and from the code vector we construct an output vector, and the aim is to make the output vector as similar as possible to the input vector. The activities of the hidden units in the code vector form a bottleneck, so the code vector is a compressed representation of the input vector. If the hidden units and the output units are linear, then an autoencoder like this will learn codes that minimize the squared reconstruction error, and that's exactly what principal components analysis does. It will get exactly the same reconstruction error as principal components analysis does, but it won't necessarily have hidden units that correspond exactly to the principal components. They will span the same space as the first n principal components, but they may be a rotation and skewing of those axes. So the incoming weight vectors of the code units, which are what represent the directions of the components, may not be orthogonal, and unlike principal components analysis, they will typically have equal variances. But the space spanned by the incoming weight vectors of those code units will be exactly the same as the space spanned by the m principal components. So in that sense, this network will do an equivalent thing to principal components. It's just if we use stochastic gradient descent learning for this network, it will typically be much less efficient than the algorithm used for principal components. Although if there's a huge amount of data, it might actually be more efficient. The main point of implementing principal components analysis using backpropagation in a neural net is that it allows us to generalize principal components analysis. If we use a neural net that has nonlinear layers before and after the code layer, it should be possible to represent data that lies on a curved manifold rather than a linear manifold in a high-dimensional space. And this is much more general. So our network would look something like this. There'd be an input vector, and then one or more layers of nonlinear hidden units. Typically we'll use logistic units. Then there'll be a code layer, which might be linear units. And then following the code layer, there'll be one or more layers of nonlinear hidden units. And then there'll be an output vector, which we train to be as similar as possible to the input vector. So this is a curious network in which we're using a supervised learning algorithm to do unsupervised learning. The bottom part of the network is an encoder which takes the input vector and converts it into a code using a nonlinear mapping. The top part of the network is a decoder which takes the nonlinear code and maps it back to a reconstruction of the input vector. So after we've done the learning, we have mappings in both directions. In this video, we're going to look at the issue of training deep autoencoders. People thought of these a long time ago in the mid-1980s, but they simply couldn't train them well enough for them to do significantly better than principal components analysis. There were various papers published about them, but no good demonstrations of impressive performance. After we developed methods of pre-training deep networks, one layer at a time, Russ Salakudinov and I applied these methods to pre-training deep autoencoders, and for the first time we got much better representations out of deep autoencoders than we could get from principal components analysis. Deep autoencoders always seemed like a really nice way to do dimensionality reduction, because it seemed like they should work much better than principal components analysis. They provide flexible mappings in both directions, and the mappings can be nonlinear. Their learning time should be linear or better in the number of training cases, and after they've been learned, the encoding part of the network is fairly fast because it's just a matrix multiply for each layer. Unfortunately, it was very difficult to optimize deep autoencoders using backpropagation. Typically people tried small initial weights, and then the backpropagated gradient died, so for deep networks they never got off the ground. But now we have much better ways to optimize them. We can use unsupervised layer-by-layer pre-training, or we can simply initialize the weights sensibly, as in echo state networks. The first really successful deep autoencoders were learned by Russ Salakudinov and I in 2006. We applied them to the MNIST digits. So we started with images with 784 pixels, and we then encoded those via 3 hidden layers into 30 real-valued activities in a central code layer. We then decoded those 30 real-valued activities back to 784 reconstructed pixels. We used a stack of restricted Boltzmann machines to initialize the weights used for encoding, and we then took the transposes over those weights and initialized the decoding network with them. So initially, the 784 pixels were reconstructed using a weight matrix that was just the transpose of the weight matrix used for encoding them. But after the 4 restricted Boltzmann machines had been trained and unrolled to give the transposes for decoding, we then applied backpropagation to minimize the reconstruction error of the 784 pixels. In this case, we were using a cross-entropy error because the pixels were represented by logistic units. So that error was backpropagated through this whole deep net, and once we started backpropagating the error, the weights used for reconstructing the pixels became different from the weights used for encoding the pixels, although they typically stayed fairly similar. This worked very well. So if you look at the first row, that's one random sample from each digit class. If you look at the second row, that's the reconstruction of the random sample by the Deep Autoencoder that uses 30 linear hidden units in its central layer. So the data has been compressed to 30 real numbers and then reconstructed. If you look at the 8, you can see that the reconstruction is actually better than the data. It's got rid of the little defect in the 8 because it doesn't have the capacity to encode it. If you compare that with linear principal components analysis, you can see it's much better. A linear mapping to 30 real numbers cannot do nearly as good a job of representing the data. In this video, I'm going to talk about applying deep autoencoders to document retrieval. There was a method developed some time ago called latent semantic analysis that amounts to applying principal components analysis to vectors of word counts extracted from documents. The codes produced by latent semantic analysis can then be used for judging similarity between documents, so they can be used for document retrieval. Obviously, if deep autoencoders work much better than PCA, we would expect to be able to extract much better codes using a deep autoencoder than using latent semantic analysis. And Russ Salakutinov and I showed that that was indeed the case. Using a big database of documents, we showed that 10 components extracted with a deep autoencoder are actually worth more than 50 components extracted with a linear method like latent semantic analysis. We also showed that if you make the code very small, having just 2 components, you can use those 2 components for visualizing documents as a point in a 2-dimensional map. And this again works much better than just extracting the first 2 principal components. To find documents that are similar to a query document, the first thing we do is convert each document into a big bag of words. In other words, we have a vector of word counts that ignores the order of the words. This clearly throws away quite a lot of information, but it also retains a lot of information about the topic of the document. We ignore words like the or over, which are called stop words, because they don't have much information about the topic. So if you look on the right, I've done the counts for various words, and they're actually the counts for the document on the left. So if you look at what words we have non-zero counts for, they're vector and count and query and reduce and bag and word. That tells you quite a lot about what the document is about. Now we could compare the word counts of the query document with the word counts of millions of other documents, but that would involve comparing quite big vectors. In fact, we used vectors of size 2000, so that would be slow. Alternatively, we could reduce each query vector to a much smaller vector that still contained most of the information about the content. So here's how we do the reduction. We take a deep autoencoder and we compress the 2000 word counts down to 10 real numbers, from which we can reconstruct the 2000 word counts, although we can't reconstruct them very well. We train the neural network to reproduce its input vector as its output vector as well as possible, and that forces it to put as much information about the input into those 10 numbers as possible. We can then compare documents using just 10 numbers. That's going to be much faster. So there's one problem with this, which is word counts aren't quite the same as pixels or real values. What we do is we divide the counts in a bag of words by the total number of non-stop words, and that converts the vector of counts into a probability vector where the numbers add up to 1. You can think of it as the probability of getting a particular word if you picked a word at random in the document, as long as it's not a stop word. So at the output of the autoencoder, we're using a great big 2000 way softmax, and our target values are the probabilities of words when we reduce the count vector to a probability vector. There's one further trick we have to do. We treat the word counts as probabilities when we're reconstructing them, but when we're using them to activate the first hidden layer, we multiply all the weights by n, and that's because we have n different observations from that probability distribution. If we left them as probabilities, the input units would have very small activities and wouldn't provide much input to the first hidden layer. So we have this funny property that for the first restricted Boltzmann machine, the bottom-up weights are n times bigger than the top-down weights. So how well does this work? We trained using bags of 2000 words on 4000 business documents from the Reuters dataset, and these documents had been hand-labelled with about 100 different categories. We first trained a stack of restricted Boltzmann machines, and then we fine-tuned with backpropagation, using a 2000 way softmax as the output. And then we tested on a different set of 4000 documents. And to test, you pick one document to be the query, one of the test documents, and then you rank order all the other test documents by using the cosine of the angles between the 10-dimensional vectors that the autoencoder gives you. You repeat this for each of the 4000 possible test documents, and then you plot the number of documents you're going to retrieve, that is how far down that ranked list you're going to go, against the proportion that are in the same hand-labelled class as the query document. This is not a very good measure of the quality of the retrieval, but we're going to use the same measure for comparing with LSA, and so at least it's a fair comparison. So here's the accuracy of the retrieval as a function of the number of retrieved documents. And you'll see that an autoencoder that's just using a code with 10 real numbers is doing better than latent semantic analysis using 50 real numbers. And of course, it's 5 times less work per document after you've got the code. Latent semantic analysis with 10 real numbers is much worse. We can also do the same thing where we reduce to 2 real numbers, and then instead of doing retrieval, we're just going to plot all the documents in a map, but we're going to colour that 2-dimensional point that corresponds to the 2 numbers produced by PCA by the class of the document. So we took the major classes of the documents, we gave those major classes different colours, and then we used PCA on log of 1 plus the count. The point of doing that is that it suppresses counts with very big numbers, which tends to make PCA work better. This is the distribution you get, and you can see there is some separation of the classes. The green class is in one place, the red class is in a slightly different place, but the classes are very mixed up. Then we did the same thing by using a deep autoencoder to reduce the documents to 2 numbers, and again, plotting the documents in a 2-dimensional space using those 2 numbers as the coordinates. And here's what we got. It's a much better layout. It tells you much more about the structure of the dataset. You can see the different classes, and you can see that they're quite well separated. We assume that the documents in the middle are ones which didn't have many words in them, and therefore it was hard to distinguish between the classes. A visual display like this could be very useful. If, for example, you saw that one of those green dots was the accounts and earnings report from Enron, you probably wouldn't want to buy shares in a company that had a green dot nearby. In this video, I'm going to describe a technique called semantic hashing that provides an extremely efficient way of finding documents similar to a query document. The idea is to convert the document into a memory address, and in that memory to organize things so that if you go to a particular address and look at the nearby addresses, you'll find documents that are very similar. This is much like a supermarket, where if you go to the location where a particular product is stored and look around, you'll find similar products. People have known for a long time that if you could get binary descriptors of images, you'd have a very good way of retrieving images quickly. Some binary descriptors are easy to get. For example, is it an indoor scene or an outdoor scene? Is it a color image or a black and white image? But it's much harder to get a list of, say, 30 binary descriptors that are more or less orthogonal to one another, which is what you really need. This is a problem that machine learning can help us with. We're going to start by looking at the equivalent problem for documents, but then we're going to apply it to images. So consider, instead of getting real valued codes for documents, getting binary codes from the word counts of documents. We do this by training a deep autoencoder that has logistic units in its code layer. That by itself is not sufficient, because the logistic units will be used in their middle ranges where they have real values in order to convey as much information as possible about the 2000 word counts. To prevent that, we add noise to the inputs to the code units during the fine-tuning stage. So we first train it as a stack of restricted Boltzmann machines. We then unroll those Boltzmann machines by using the transposes of the weight matrices for the decoder, and then we fine-tune it with backpropagation. And as we're doing that, we add additional Gaussian noise to the inputs to the code units. In order to be resistant to that noise, the code units need to be either firmly on or firmly off. And so the noise will encourage the learning to avoid the middle region of the logistic, where it conveys a lot of information, but it's very sensitive to noise in its inputs. At test time, we simply threshold the logistic units in the middle layer to get binary values. So if we can train an autoencoder like this, we will be able to convert the counts for a bag of words into a small number of binary values. In other words, we'll have learned a set of binary features that are good for reconstructing the bag of words. Later on, Alex Krzyzewski discovered that we don't actually have to add Gaussian noise to the inputs to the 30 code units. Instead, we can just make them stochastic binary units. So during the forward pass, we stochastically pick a binary value using the output of the logistic. And then during the backward pass, we pretend that we'd transmitted the real value probability from the logistic, and that gives us a smooth gradient for backpropagation. Once we've got these short binary codes, we could of course do a sequential search where for each known document we store a code, and then when a query document arrives, we first extract its code, if it's not one of our known documents, and then we compare the code with the codes of all the stored documents. The comparisons can be very fast because they can use special bit operations on a typical CPU, which can compare many bits in parallel. But we have to go through a very long list of documents, possibly billions. There's a much faster thing we can do. We can treat the code as if it was a memory address. So the idea is that we take a document and we use our deep autoencoder as a hash function that converts a document
into a 30-bit address. Now we have a memory with 30-bit addresses, and in that memory, each address will have a pointer back to the documents that have that address. If several documents have the same address, we can make a little list there. Now, if the autoencoder is successful in making similar documents have similar addresses, we have a very fast way of finding similar documents. You simply take the query document, you go to the address in memory that corresponds to its binary code, and then you look at nearby addresses. In other words, you start flipping bits in that address to access nearby addresses. And you can imagine a little Hamming ball of nearby addresses that differ by just a few bits. What we expect to find at those nearby addresses is semantically similar documents. So we've completely avoided searching a big list. We simply compute a memory address, flip a few bits, and look up the similar documents. It's extremely efficient, especially if we have a very large database of, say, 1 billion documents. We've completely avoided the serial search through 1 billion items. I sometimes call this supermarket search, because it's like what you would do in a supermarket. Suppose you went to an unfamiliar supermarket and you wanted to find anchovies. You might ask the teller at the supermarket, "Where do you keep the cans of tuna fish?" You'd then go to that address in the supermarket and you'd look around. Hopefully near there's things like cans of salmon and maybe cans of anchovies. Of course, if you're unlucky, the anchovies might have been stored in a completely different place next to the pizza toppings. And that's the downside of this kind of search. Now in a supermarket, it's essentially a 2D surface. So it's really a 1D string of shelves which have height, and that gives you 2D. And so you only have 2 dimensions in which to locate things. And that's not sufficient to put all the things you'd like to be near one another. You'd like, for example, to have the vegetarian version of things nearby, or the kosher version of things nearby, or the slightly out-of-date version of things nearby. And in 2D you can't do all that. But what we have here is a 30-dimensional supermarket, and that's a hugely more complex space, where it's very easy to have things near an item for many different reasons, because of similarity along many different dimensions. Here's another view of what we're doing in semantic hashing. Most of the fast retrieval methods work by intersecting stored lists that are associated with queues extracted from the query. So Google, for example, will have a list of all the documents that contain some particular rare word, and when you use that rare word in your query, they will immediately have access to that list. They then have to intersect that list with other lists in order to find a document that satisfies all the terms in your query. Now, computers actually have special hardware that can intersect 32 very long lists in a single machine instruction. The hardware is called the memory bus. So each bit in a 32-bit binary address specifies a list of half the addresses in memory. For example, if the bit is on and it's the first bit in the address, it specifies the top half of memory. If the bit is off, it specifies the bottom half of memory. What the memory bus is doing is intersecting 32 lists to find the one location that satisfies all 32 values in the binary code. So we can think of semantic hashing as a way of using machine learning to map the retrieval problem onto the type of list intersection the computer's good at. As long as our 32 bits correspond to meaningful properties of documents or images, then we can find similar ones very fast with no search at all.
In this video, I'm going to talk about the use of binary codes for image retrieval. For retrieving documents, people like Google have such good methods already that techniques like semantic hashing may not be of much value. But retrieving images is much more difficult, and methods that convert an image into a fairly large binary code of, say, 256 bits seem to work quite well. However, we don't want to do a very long sequential search through vectors of 256 bits. So semantic hashing can be used to first create a shortlist, and then we can get better quality matches by using longer binary codes in a serial search.
Now we're going to look at using binary codes for image retrieval. Image retrieval at present is typically done using the captions. But why not use the images too? They obviously contain a lot more information than the captions. The basic problem is that pixels are not like words. Individual pixels don't tell us much about the content of an image. Obviously, if we could recognize the objects in the images, then we'd have things that were much more like words. But recognizing objects is hard. At least it was when we first did this work. Now deep neural nets have got much better at it, and so that may well be the way to go. So if we're not going to recognize the objects, maybe what we should do is extract a vector that has information about the content of the image, and the obvious thing to extract is a real-valued vector. But the problem is that matching real-valued vectors in a big database is slow, and it also requires a lot of storage for the real-valued vectors. If we can extract a fairly short binary vector that contains a lot of information about the image, that's much easier to store and much faster to match. Even faster is to use a two-stage method. So first we extract a short binary code of about 30 bits, and that short binary code is used with semantic hashing to very rapidly get us a short list of promising images. So we simply take the short binary code and flip a few bits in it to get candidate images. The candidate images can then be matched using 256-bit binary codes that are stored with each known image to search for much better matches than can be found with a 28-bit binary code. Even a 256-bit binary code only requires 4 words of memory per image. And even though we're then going to do a serial search on these binary codes, the search can be done very fast because it only requires a few operations to compare two 256 binary codes to find out how many bits they have in common. The question is, how good is a binary code of that size at retrieving images? Are they going to find images that we think of as being similar? So here's a net that was trained by Alex Krzyzewski. It's working on small color images, so they're only 32 pixels by 32 pixels, and it takes as input the red, green and blue channels from those images. So there's 3,000 inputs. It then expands that to a larger number of hidden units, because we're going to go from real valued inputs to logistic hidden units, which probably have less capacity. We then progressively decrease the number of units in each layer until we get down to 256 bits. This encoder has about 67 million parameters. It's quite big. It takes a few days to train it on an NVIDIA GPU, and Alex trained it on 2 million images. There's absolutely no theory to justify the architecture he used. We know we want a fairly deep net. It makes sense to make it get narrower as we go up, but this particular architecture, where you halve the number of units each layer, is just a guess. The interesting thing is, a guess like this already works quite well, and presumably there are some other architectures that will work better. The first question to ask is, how well does an autoencoder like this do at reconstructing the images? So here's a face image and its reconstruction. And you can see that from the reconstruction you can tell what kind of an image it is. Here's another example where it's a scene, probably at a party. You can't really tell what kind of a scene it is from the image, but you might guess that there are a number of people involved, or you might not. Here's an outdoor scene, and you can see that the reconstruction captures a lot of information about the outdoor scene. It captures the water and the sky, and the fact that there's a thin strip of land. So let's look at the quality of retrieval we can do with an autoencoder that gives those kinds of reconstructions. We'll start with a picture of Michael Jackson in the red square, and Alex retrieved the most similar images, and above each image you can see how many bits it differed from Michael Jackson by. And you'll notice they're all a fairly similar number of bits. In 256 bits, differing by only 61 bits is extraordinarily unlikely to happen by chance if they were random images. It has to be a pretty similar image to differ by so few bits. One nice thing about what's retrieved is, with one exception, they're all faces. If we look at the retrieval you get by using Euclidean distance on the raw pixels, then some of them are faces, but most of them aren't. So obviously the autoencoder has understood something about faces that isn't in the information about Euclidean distance. It's clearly giving much better retrieval. Let's take another example. Here we took the image of the party scene and retrieved other images, and you can see that about half of them have images you would think of as fairly similar. They're other party scenes. They're typically other party scenes with something bright in the middle, like the original party scene, and you'll notice that most of the bad matches also have something bright in the middle. So even though we're getting down to 256-bit binary codes through a lot of hidden layers, it's still sensitive to quite a lot about the image structure and where the brighter patches are. If you look at what Euclidean distance does, it's much worse. Euclidean distance gets one other scene with a group of people, and then everything else is fairly dissimilar. You'll notice with Euclidean distance, it often gets very smooth images. That's because if you can't match the high frequency variation in the image, it's better to match its average than to get other stuff with high frequency variation that's out of phase. So when you've got a complicated image, Euclidean distance will typically find smooth images to match it. And that's because it's minimizing a squared error in pixel space. So obviously we'd like the image retrieval to be more sensitive to the content of the image, that is to the kinds of objects and their relationships in the image, and less sensitive to the pixel intensities. We can do that by first training a big net to recognize lots of different kinds of object in real images. And we saw how to do that in Lecture 5. Then we take the activity vector in the last hidden layer of the big net and use that as a representation of the image. This should be much better than the pixel intensities at capturing information about the kinds of objects in the image. So to see if this approach is likely to work, we use the net described in Lecture 5 that won the ImageNet competition. So far we've only tried it on Euclidean distance between the activity vectors in the last hidden layer. But obviously if it works for that, we could then take those activity vectors and build an autoencoder on those to get them down to binary codes. So let's first see if it works with Euclidean distance. It turns out it works really well. We don't know yet whether it'll work with binary codes. So in the column on the left, you see the query images, and then to the right of them, you see all the things that were retrieved. If you look at the elephant query image, you'll see that what gets retrieved is other elephants, but elephants with very different poses. So those images wouldn't have a very good overlap in pixel space, although the overlap wouldn't be that bad. If you look at the Halloween pumpkins, you'll see that all the retrieved things are other Halloween pumpkins, and some of them would have a pretty bad overlap in pixel space. Similarly with the aircraft carrier, we retrieve other images of aircraft carriers that are very different. So we anticipate that if we could reduce these activity vectors to short binary codes, we would have a fast and effective way of retrieving similar images just by the content of the image. We'll see in Lecture 16 that we could actually combine the content of the image with the caption of the image to get an even better representation.
In this video, I'm going to talk about alternative pre-training methods for learning deep neural nets. I introduced pre-training using restricted Boltzmann machines trained with contrastive divergence. But after that, people discovered there are many other ways to pre-train layers of features. And indeed, if you initialize the weights correctly, you may not need pre-training at all, provided you have enough labeled data. We've seen some of the neat things that can be done with the codes produced by deep autoencoders. I now want to consider shallow autoencoders that just have one hidden layer. Restricted Boltzmann machines can be viewed as shallow autoencoders, particularly if they're trained with contrastive divergence, because they're trying to make the reconstructions look like the data. When viewed as an autoencoder, a restricted Boltzmann machine has very strong regularization,
because the hidden units are only allowed to have binary activities, and this restricts their capacity a lot. If we train restricted Boltzmann machines with maximum likelihood, they're not at all like autoencoders. One way to see that is if you had a pixel that was pure noise, an autoencoder would try to reconstruct whatever noise value it had. A restricted Boltzmann machine trained with maximum likelihood would completely ignore that pixel and model it just using the bias for that input. So since we can view a restricted Boltzmann machine as a kind of strongly regularized autoencoder, maybe we can replace the RBMs that we use for pre-training with a stack of autoencoders. It turns out that if you do that, pre-training is not as effective. At least that's true if you use shallow autoencoders that are regularized just by penalizing the squared weights. So stacking these autoencoders doesn't work as well as stacking restricted Boltzmann machines. However, there's a different kind of autoencoder that does work as well, and that's the denoising autoencoder that's been studied extensively by the group in Montreal. Denoising autoencoders work by adding noise to each input vector by setting many of the components to 0, but it's different components for different input vectors. This resembles dropout, but it's for the inputs rather than the hidden units. The denoising autoencoder is still required to reconstruct the inputs that have been set to 0, and so it can't just copy its input. The danger with the shallow autoencoder is that if you give it enough hidden units, it might just copy each pixel to one hidden unit and then reconstruct that pixel from that hidden unit. A denoising autoencoder clearly can't do that. So it has to use hidden units to capture correlations between the inputs, so that it can use the values of some inputs to help it reconstruct the inputs that have been zeroed out. If we use a stack of denoising autoencoders, pre-training is very effective. There's some cases in which RBMs still work better, but in most cases denoising autoencoders are more effective. It's also much simpler to evaluate the pre-training using a denoising autoencoder, because we can easily compute the value of the objective function. When we pre-train a restricted Boltzmann machine with contrastive divergence, we can't compute the value of the real objective function we're trying to minimize, so we often just use the squared reconstruction error, which is not actually what's being minimized. In a denoising autoencoder, we can print out the value of the thing we're trying to minimize, and that's very helpful. One disadvantage of the denoising autoencoder is that it lacks the nice variational bound we get with restricted Boltzmann machines, but that's only of theoretical interest because it only applies if the restricted Boltzmann machine is trained with maximum likelihood. Yet another kind of autoencoder is the contractive autoencoder that was also developed by the group at Montreal. The way this works is that we try to make the hidden activities be as insensitive as possible to the inputs. Of course, the hidden units can't just ignore the inputs altogether because they have to be able to reconstruct them. The way we achieve this insensitivity is by penalizing the squared gradient of each hidden unit with respect to each input. So we try and make each hidden unit so that it won't change much if we change an input value. Contractive autoencoders also work very well for pre-training. Their codes tend to have the property that only a small subset of the hidden units are in their sensitive range. For different parts of the space, it's a different subset, and so this active set acts like a sparse code. The other hidden units are all saturated and are insensitive. RBMs actually have a very similar behavior. After they've been trained, many of the hidden units will be saturated, and the working set of unsaturated ones will be different for different training cases. I want to finish by summarizing my current view of pre-training. There are now many different ways to do layer-by-layer pre-training that discovers good features. When our dataset does not have a huge number of labels, this way of discovering features before you ever use the labels is very helpful for the subsequent discriminative fine-tuning. It discovers the features without using the information in the labels, and then the information in the labels is used for fine-tuning the decision boundaries between classes. It's especially useful if we have a lot of unlabeled data, so that the pre-training can do a very good job of discovering interesting features using a lot of data. For very large labeled datasets, however, initializing the weights that are going to be used for supervised learning by using unsupervised pre-training is not necessary, even if the nets are deep. Pre-training was the first good way to initialize the weights for deep nets, but now we have lots of other ways. However, even if we have a lot of labels, if we make the nets much larger again, we'll need pre-training again. So an argument I often have with people from Google is they say we've got lots and lots of labeled data, so we don't need regularization methods. Our nets won't overfit anyway because we've got so much data. The counter-argument is, that's only because you're using nets that are much too small. You should use much, much bigger nets on much, much more powerful computers, and then you'll start overfitting again, and you'll need these regularization methods, like dropout and pre-training. If you ask which regime the brain is in, the brain is clearly in the regime where it's got huge numbers of parameters compared with the amount of data it's got. And so for the brain at least, regularization methods are very important.